everybody. See if I can stay. So let's see. So the next problem set's available. I have my usual office hours. We'll have one more problem set. So you should be paying attention to sure, thinking about your final project again. If you need any assistance or like to discuss with me in any way some ideas, I'm happy to do that. So just let me know. All right. Very good. All right. So last time we were talking about the problem of spontaneous emission. And we were contrasting two different physical situations. In the context of the James-Cummings model, we were looking at a situation where we had our two-level atom inside a very, very high-quality cavity, super-duper reflecting and very low absorption and very long lifetime states, in which case we, in the very strong coupling regime, we just think about it as a single mode of this magnetic field, that mode in the cavity that is coupled to our field. And in the particular case that I'm expressing over here, this is the particular case where I'm exactly on resonance, where the cavity is tuned to be exactly on resonance with the atom. And if we start the atom in the excited state, then the field in the vacuum with no field at all, then we know the dynamics of that system is one that the atom at some point later in time will be in the ground state, and there'll be exactly one photon in the cavity. And then at a later time, the atom will absorb the photon, and with unit probability be back in the excited state with no photons in the cavity. And we can write down under these approximate case situation in the strong coupling regime, we know what the dynamics of that system exactly is. We would have Rabi oscillations, what are called vacuum Rabi oscillations, between the atom in the excited state and no photons and the atom in the ground state and exactly one photon in the cavity. And it would just go back and forth with the frequency of 2 times the coupling constant G. 2G is the Rabi, what was sometimes called the vacuum Rabi frequency. Okay? And this is a completely reversible dynamical evolution. Okay? In contrast, if we are now in free space, then we know that that kind of evolution will be such that if I start the atom in the excited state with no photons around, then at a later time, asymptotically far into the future, asymptopia isn't very far into the future, depends how short the lifetime is, the atom will be in the ground state and the photon will fly away. And so we'll have one photon freely flying away, okay? Come back to that hopefully later in the lecture. And we expect that we should describe the evolution here, the probability that the atom is in the excited state will decay exponentially fast with a rate gamma, which is the spontaneous emission rate, also known as the Einstein A coefficient. And that's quite a different type of evolution from this, okay? So we want to derive this as obviously an approximate solution, right? Because this evolution is not consistent with unitarity. This is not a unitary evolution. So it's only got to be approximately true, and it's a really difficult thing to get this exactly right, to understand all the different approximations. We'll talk about it today, but we'll revisit it again in some more detail next semester. But again, as I mentioned at the end of the last lecture, you should think about this equivalently to the way in which we think about entropy increasing in a closed quantum system. I mean, you know, Boltzmann crazy, but the idea that you can have microscopically reversible equations of motion, yet see effective evolution which is irreversible, is a hard problem in physics to deal with. All right, so we're going to attempt it today and see how that comes about. And we're looking now at the situation where we have our two-level atom in the vacuum, which we describe here by this Hamiltonian. This is the two-level approximation. We're talking about the dipole approximation and the rotating wave approximation, which are all good approximations for describing this effect. So under those approximations, the QED Hamiltonian reduces to a fairly simple Hamiltonian that involves the free field, which is just a bunch of harmonic oscillators for all the plane wave modes. We have the atomic Hamiltonian, which is just my two-level Hamiltonian, and then the interaction Hamiltonian, which is written here in the rotating wave approximation. Okay. And so we want to do this kind of solution. We want to solve for the evolution of the total state of the system, where now we have, in contrast to what we had in the James Cummings problem, we have all of the modes of the field to worry about. And so to do that, and to do the approximations most effectively, it's convenient to go to the interaction picture. So you may remember, the interaction picture in quantum mechanics is a kind of halfway house between the Schrödinger picture and the Heisenberg picture. In the Schrödinger picture, the operators are constant unless there's an explicit classical time-dependent field, and the state evolves in time. In the Heisenberg picture, you make the state fixed in time, but you let the operators unitarily evolve according to the total Hamiltonian. In the interaction picture, you kind of divide it up, and you say the operators evolve according to the free evolution. That's this. And the states evolve according to the interaction Hamiltonian in the interaction picture. So I hope you studied that in the context when you took your 522 and learned all about time-dependent perturbation theory. What we're doing here is effectively a version. We're going to go a little bit beyond time-dependent perturbation theory. All right, so this is our Hamiltonian in the interaction picture, and it's the thing that is the generator of the dynamics of the state in the interaction picture. All right? So let's do it. So this is our Schrodinger equation. And we want to write this. Now, in this problem, we know because of the rotating wave approximation, we know that the total excitation in the system, that is, the number of atoms in the number, right, whether or not the atoms in the excited state, plus the total number of photons in the system is conserved. So that means that if we have an initial state that has a fixed value of this total excitation, only the other states that have the same total excitation are coupled through the Hamiltonian, right? And so if we start initially in the excited state and the field in the vacuum, then the only other states can have only one excitation. And the only other states that have one excitation are the states with the atom in the ground state and one photon in some mode. Okay? The difference between what we have here and what we had in the Jaynes-Cummings problem is we only had one mode before, but now I have all the modes of the field. Okay. So that means I can write an ansatz, and I love to say the word ansatz, that the total state of the system is going to have some probability amplitude to be in the excited state with no protons in the field, that is, say, in the vacuum, or I could have some probability amplitude to be in one of these states. So that's all we can have according to the Schrodinger equation. And still the Schrodinger equation. Yeah. I'm not gonna put this little label, the superscript I, to say that we're in the interaction picture. We're in the interaction picture. Okay? As our acting chief of staff said, get over it. We're in the interaction picture. All right. I'm gonna keep politics away from my topics. It's irresistible. All right. So what we're going to do now is just solve. We're going to write down differential equations for these amplitudes. Okay. So that's another way. I mean, the way we could have solved this problem that way as well. In this case, we, just were able to, because we're so clever, look by eye and write down the unitary operators in terms of SU2 and all of that. We're going to not be able to do that because we got this whole bunch of modes, and we're going to solve this using differential equations. Okay? So the amplitude here changes as a function of time according to the Schrodinger equation, where this is in the interaction picture. Right? That's just this equation projecting out that particular amplitude. And then we put this on the right-hand side, use the interaction Hamiltonian, and what do we get? Well, the only terms here are the ones that lower the atom and create something in the field. So this is going to be minus I, the coupling constant, times CG with one photon in that mode. The ground state evolves. Sorry, the amplitude there. We'll have to sum over all the modes, sorry. This picks off a specific guy, and that's minus G. This guy is associated, let's see, which one is this? This guy was the guy that created photons. So this guy had a star, and this guy doesn't have the star. And I have to have the time dependence there. I forgot to put that in over here. So this is e to the plus omega k minus omega eg t. And this is equal to C0 at t e to the minus I omega k. All right, now, there's so much algebra in what comes up, I will be a fool to try to do this on the fly. So I'm going to make sure I have my notes handy so I can get it right. Yeah, I knew I got it backwards. Okay, let me step back a second. I plug this in here. When this guy acts on this, and I'm projecting on E0, it's the thing that annihilates a photon and raises this that picks up that term. Right? So this should be the other way around. Okay. Now I'm happy. All right, so what we have here is a coupled set of ordinary differential equations, and we just have to solve them.
Should there be a summation on that bottom line?
No, there's no summation here because I'm picking up a particular, so formally I put in a dummy index here, and I'm just picking off that for this, I'm looking at this for this specific mode. So there's no sum there. Okay, so we have a coupled set of ODEs here that we need to solve. If we had just a single mode, again, I want to emphasize, if we had just one mode here, this would just be two coupled ODEs. And the solution to this equation would be this. It would be simple to solve. But this is not that. We have this infinite set of coupled ODEs, and solving them is not possible exactly. All right, but we can do the following. Firstly, I can just formally integrate this. So this tells me that the amplitude here at some later time, I have the initial condition, which is 0. There's no amplitude here at time t equals 0, right? So we have the initial conditions that this is 1, and this is 0 for all of the modes. So this then is equal to the integral. So just factor out the constant, 0 to t dt prime c e to the minus I omega k t prime c e0 t prime. So that's just a formal integration. I didn't solve anything because I don't know what this is. But I could just do that, just integrate it with with that initial condition. And then I can plug this back into here. And I get that this is equal to minus the sum over the modes, the absolute value of the coupling constant squared. And then I have the integral from 0 to t dt prime e to the minus I omega k minus eg t t minus t prime c e0 dot t prime. So that's kind of, we're basically there, almost. I guess I got plus, there should be a plus sign here. From that guy. So this is a formal solution. It's not an actual solution to the differential equation, or there's no way to solve this. It's an integro differential equation, because we got this thing on the right-hand side that's this, which depends on its whole history from 0 to t. So this is nothing more than just a restatement of the differential equations. It's not an actual solution to anything. However, we can start thinking about approximations to this. So I just want to, let's just do a little bit of a precursor. I can think about this as the following thing. Let me write this as an integral dt prime of something I'll call k of t minus t prime, where k of tau is equal to the sum over the modes g k squared e to the minus I omega k eg tau. Right? You agree with that? So, what can we say about this kind of expression? Well, really the whole question, this whole thing is sometimes called the memory kernel. The question is, in its interaction of the atom with the field, how much memory does the system have of what it was doing over the whole history from 0 to t? If the whole point of spontaneous emission is that there is a separation of timescales. Okay? And this is where it seems like one is being fast and loose with approximations, but it all revolves around the idea of a separation of timescales. What are some different timescales in the problem? Well, one, we're going to ultimately see there's some timescale which is gamma. This is the lifetime. And what we expect to see in our calculation is that this amplitude is going to change on this time scale if we ultimately do it right and be self-consistent, that there is a time scale for which the probability amplitude to be in the excited state is going to change, and that is going to change at on a time scale related to the spontaneous emission rate. Okay. But there's another time scale in this problem, let's come back to this board, which is, well, you know, if I come back over here, inside this cavity, this photon was confined. It was, in principle, if I had a perfect cavity, it would stay there forever. In which case, you know, I can put a photon in the cavity and wait, and then send another atom through the cavity, and that atom would feel that photon. And if it's the same atom sitting there, it's just going to go back and forth. In some sense, there is a correlation time between the atom in the field, and that correlation time in this problem is infinity, assuming the cavity has an infinite lifetime, because it will always be there. Whereas in this case, what's going to happen to the photon? It's going to leave. It's out of there. It's going to fly away at the speed of light. That's pretty damn fast, as fast as we go. And the photon, in some sense, once it's gone, unless somehow there's some other mirrors that come back sometime, we expect the correlation time of the field with the atom to be incredibly short. Something like the time it takes for light to propagate across the size of the atom, which is an angstrom size, and that's going to be an attosecond. So that's an incredibly short time scale compared to the time scale over which the atom actually decays. So this is one time scale, and the other time scale is the correlation time. Between the atom and the field. And when this, so what we, because these can be extremely well separated, this might be an attosecond, and this might be some tens of nanoseconds, or some few nanoseconds. That's many orders of magnitude separation between these time scales. And so the whole point of how we're going to get the rabbit in the hat, or out of the hat, I don't know. But there's a hat, there's rabbit, there's magic. From something which is reversible to something that is irreversible is that we're going to coarse grain over the time of the correlation time and throw away any information of what's going on within that time scale. And that's basically because we're going to throw away that information, the system loses its ability to recover and becomes irreversible. Okay? So the idea here is we're going to look at times that are absolutely huge compared to the correlation time, but tiny compared to the lifetime. And we can do that because of the separation of time scales. And that's really the whole story. And under that case, what we will see is that the real part of this kernel function will be proportional to a delta function in time. It's not really a delta function in time. It's something which has a width that is on the order of the correlation time, because that's the time scale over which the system, the field, and the atom remember each other. But we're basically taking that time to be effectively zero for our problem and not taking into account. And this is known as the Markov approximation. which we mentioned early in the semester when we were reviewing some aspects of stochastic probability theory, right? So, you know, as a precursor, yeah.
I'm confused because, you know, in the lecture notes, you're going to say that it's also a delta function in omega.
I am. This is why I don't like to, I don't want to be cut to, you will wait to see. I don't always do things the way they're written in the notes. And that's why I don't like to bring out the notes until I have the lecture. Because otherwise, we didn't do it the way you said in the notes. I can't, so let's wait and we'll see how it's all going to go. Okay, so let me develop the ideas the way I want to at the moment and we'll connect it. Someone else like, yeah.
What happens to G? Jeff, we're just one?
This guy?
Yeah.
Yeah. So that's a very good question. So really, this the ability to have this separation of timescales is related to the fact that we're effectively doing a kind of perturbation theory. So this ability says that we have a weak coupling between the field and the atoms. Okay, that's known as the Born approximation. So this derivation is sometimes called the Born-Markov approximation. You may have learned about the Born approximation in the context of scattering theory. It's rarely taught anymore, but you might have learned that. That's why it's called the Born-Markov approximation. But the point here is that all of these guys, and we're going to talk about this, are tiny compared to the bare. So this is the interaction strength. And this is the free time scale or energy scale. Okay, so this was just a little precursor. We'll come to we're going to go through let's discuss the notes now and see how it all comes together. So ultimately, if this is true, just as a precursor here, what we're going to see is that if this is true, what we'll find is that actually what we will see is that this guy will look like this, approximately, under the Born-Markov approximation. We will see that the probability amplitude will decay with a rate gamma over 2, so that the probability decays at the rate gamma. And in addition, there will be a phase shift, which is a component of the Lamb shift. All right, so let's return to where we were over here and see how we're going to get there. Well, the first thing we need to do is deal with the fact that we have this sum over modes, and that sum was put there because we put on an artificial quantization volume. And that quantization volume is a fiction of our mathematics. There is no volume that we are considered, that it actually exists in physical space. It's not that the atom is in this giant cavity with some volume. We just put boundary conditions so that we can count the modes. And so in order to do that, to remind you, what we do is to deal with the sum. So we want to consider the volume going to infinity. We want to take the boundary conditions all the way to infinity. So in order to do that, we're going to say, all right, my sum over all the modes now is going to become an integral over a continuum of modes, but I'm going to put on a factor which tells me what the density of states is. So this is equivalent to thinking about if I wanted to do some kind of sum over all the molecules in matter. Instead of that, I can think about there's some continuum of density of matter. And then within a particular volume, that tells me how many of those molecules I have, right? This is, of course, a standard procedure that I assume you have seen in StatMech or something like that. So, to remind you, we have our quantization volume that had some length Lx, Ly, and Lz. And our modes were some quantization as such. And so in reciprocal space, or case space, what we have is a mode on a lattice of possible spaces depending on the value of this nx, ny, and z, right? And so so what we have is the density of states is uniform, and we have one mode for a given polarization within a volume of case space, which is this, right? So this is at, the first mode is at one of these, the second mode is at two of those, and if I think about that, I have one mode in this volume in case space. So my density of states then is in case space is this. Now, at the end of the day, if you come back over here, my integral here, if I think about both g sub k and this, what I really care is about thinking about this in terms of the magnitude of k and the direction of k. So it's convenient to think about this in spherical coordinates in a certain shell in case space that has a particular width, right? And so I can think about my d cubed k, which is over here, dk, as an integral of k squared dk d solid angle dk. All right. Okay. So let's continue. I need to do the sum is going to be integral d cubed k, which now becomes dk times k squared times the magnitude, the integral d omega sub k, g k lambda squared times the density of states. Plug that in, and I'm going to get the integral. So G, remember this guy was equal to the coupling constant. So we plug that in. So that's g squared here, and then I get, dk times k squared. The integral over the directions of propagation. Here, d over 2 pi cubed. Integral over the direction of propagation, dEg dot polarization. And then I have to have the sum over all the polarizations. So I have to have the sum over all the polarizations. All right? Very good. So, firstly, we can do this integral. How are we going to do that integral? Well, this is the integral over all the directions of propagation of the polarization, which depends on the direction of propagation, knotted into the dipole moment. So, let's say we have a particular direction of propagation, right? I'm going to choose for convenience here linear polarization. I could use circular, but it's not very convenient for this purpose. So I have two modes. I have one in the plane and one out of the plane of polarization. Okay, so that's epsilon to k for lambda 1, and this is for lambda 2. And I have to dot that into the dipole. I could choose the dipole direction, any direction I like relative to k, because I'm integrating over all directions of k, right? So I might as well call the polar axis here for the k direction to be the direction of the dipole moment. I can choose it any way I like because I'm integrating over all directions. So I'm going to choose the polar axis to be the direction of the dipole moment. Okay? And this is the polar angle theta. We have, of course, the azimuthal angle phi. All right? So, the sum over the sum over lambda of dk dot this then is what? Well, I have to sum over the two polarizations. What's the dot product of this polarization with the dipole? You got it, it's out of the board. 0. It's orthogonal. It's out of the board. This is in the plane, right? And what is it? So, and what is the? So this is, you know, my p polarization, and that's my s polarization. The s dotted into 0. The p polarization is what? Sine theta, right? So it's the magnitude of this times the sine of theta. Okay. So then I have to do this integral. Integral d omega of sine squared theta. You could do that integral. Of course, that's equal to 2 pi d cosine theta. It's equal to 2 pi times 4/3 when you do it. All right. So when we put all of this together, this of course times the magnitude of this guy squared. We get the following. This is equal to an integral. I'm going to also, for convenience, turn this into an integral over omega. So k is omega over c. And so I just change variables there. This is equal to an integral over d omega. And then I got stuff. Let's see. I got 2 pi times 4. So I better get my notes. Get up wrong. Come do not run the board. Do. Right. That's right. Third, there is factor of 2 up front. Yeah, I think that's right. Okay, so let's just do a little bit. We see what we have over here once again. Let's come back to this board over here, right? This, by turning the sum into an integral, I can bring this guy out, right, e to the minus I. Where this guy is proportional to omega to the 3rd. So that was just taking all of this, what we have over there, right? And the only dependence we have left is something that goes like omega to the 3rd power. This came from our density of states in frequency. Once we've done all the integrals over all the directions of propagation. And this issue about the Markov approximation is ultimately related to how broadband is this function. If this were a flat function of omega, if this didn't change at all with omega, then this would be a delta function. So the correlation time is intimately related to the how this is changing with respect to frequencies. Ultimately, of course, there's got to be some cutoff here. But this is a very, very slow function of omega compared to something else. And that something else is where we're headed next. Okay. So let's see where we are. Let's leave this board here and let's work on this board. Oh, I want to make one point before I go on. Notice, what happened to the quantization volume? It canceled, as it should. The ultimate solution should not depend on the quantization volume. Right? And where did it cancel? Well, this was the coupling constant, but this was the density of states. They're inversely related to one another. So at the end of the day, by putting in the density of states factor, I cancel out the quantization value, as I must. All right, so let's come back to our expression over here. We have C of e sub 0 dot is equal to an integral over all the frequencies. This thing I'm going to call this. And then the integral 0 to t prime, e to the minus I omega k, e g t minus t prime, c 0. Note, I haven't made any approximations yet, other than the ones we initially started with, the rotating wave approximation, the dipole approximation. This is still a formal solution. It's not an actual solution. But now's where the approximation comes in these time scales. So because this is so broadband, and we have frequencies that are going to be very, very big in this problem, whereas this we're taking to be slowly varying on these time scales. We're going to say this integral will vanish unless t is close to t prime. In which case this is no longer a rapidly oscillating function compared to this. That's related to the Born approximation. The Born approximation was saying that this is a slowly varying function compared to these time scales. And under that approximation, in the same way that we did when we thought about adiabatic evolution, we were going to take this outside the integral and say that this thing really only has contributions when t is close to t prime. That's it, a rabbit's in the hat. Yeah, You say, is that really valid? Well, again, it's really a question of going back to how we developed these ideas, whether this function, if I integrated this over omega, what was the kernel's correlation time? And if that correlation time is extremely short compared to the time scale over this changes, I can make that approximation. But I have, by doing that, sorry, I'll use these two fingers, I have effectively thrown away the whole history of what happened between 0 to t. In this way, I have coarse-grained and made the problem irreversible. Now, you may have studied something similar in your previous studies in quantum mechanics, which is time-dependent perturbation theory. In time-dependent perturbation theory, you just say this was equal to what it was at the initial time. You say this is 1. And you just fix that. And then you get Fermi's golden rule. By keeping this and saying, no, it's not 1, but it's just coarse-grained, it's what's known as the Wigner-Weisskopf approximation, which is a slightly more sophisticated version of time-dependent perturbation theory. All right, so now let's take a look at this again. Let's now, once I've taken this outside under this Born-Markov approximation, let's do this integral. So this integral is equal to e to the minus I omega k minus omega g t minus t prime over minus I or plus I omega k minus omega g going from 0 to t, which is equal to right, 1 minus e to the minus I omega k minus omega g t over this. Right? Which is, so this is t prime. So I can factor out a half of that phase, multiply, divide by 2, multiply by 2, and this becomes the sinc function. Right? Remember, the sinc function is sine x over x. All right. So let's take a look at what's going on here inside this interval. As a function of frequency, I have this cubic thing, and then I have the sinc function. Yeah?
There's a t in the denominator, like then can you call that as sink?
There's a t in the denominator, but that's in the sink.
On the next, other side of the equal sign.
I'm not
The
following.
1 minus e to the,
Yeah.
So we need a t there, right, to convert.
Here?
Yeah.
No, I'm integrating with
Yeah,
respect
so
to
but
t.
then how can you call that a sink?
Ah, good point. I need a t in the, I need to put a t in the numerator. Right? Yes. Absolutely. All right. That function, the sink function, looks like this, with a width that is proportional to 1 over t, and as Shiva rightly noted, has a height that is proportional to t, right? And here's where this separation of timescales comes in yet again. We want to look at timescales that are extremely long compared to the correlation time of the atom of the field, though short compared to the timescale over which the probability amplitude really changes. And we can do that because we see here that as long as my time here is much, much longer than the correlation time, which is the inverse. I mean, this thing goes up and up and up, and then some cutoff comes down. That this looks like a delta function. This is like a spike compared to this in frequency space. So we have both of those things. We have both this delta function in time and this delta function in frequency. Let's see here. You may have seen this limit in Fermi's golden rule. And Fermi's golden rule seems totally nuts when it's derived, because you do time-dependent perturbation theory. You say, my probability amplitude is this, and it doesn't change because it's a weak perturbation. But then you take t to infinity. You say, what the heck? How can I take t to infinity? At infinity, it's not a perturbation anymore. I mean, what's going on? But it's really not that t is going to infinity, it's that this is true. And so it's infinite with respect to this, but tiny, absolutely tiny compared to this. So when we say t equals infinity, we really mean this. So with that said, because in this integral, that width is so small, I can take t to infinity. That's my other magic trick. The two magic tricks was to take this outside the integral and get rid of the prime, and the other one is to say the contributions beyond that are negligible. We can take t to infinity from there. And now we can solve it. So let me write this then. I'm going to define zeta of omega k minus omega eg as equal to the integral from 0 to infinity of e to the minus I omega k minus omega eg tau e tau. Actually, this should be plus. So when this is infinity, so I'm going to distribute that minus sign. And then t prime minus t, I'm going to call tau. And I can just change the integral to tau. All right? So let's do that integral. How do you do that integral? Yeah, that's a good way to go. We're on a desert island. No bars on my cell phone. I lost my copy of Jackson at Sea.
Put in a regularizing.
Put in a regularizing function. This, of course, is not, this doesn't converge. But what we can do is we take the limit of this as with some small parameter such that we put on a cutoff. It's one way of solving this integral, right? So this then is equal to 1 over I k minus epsilon e to the minus I k minus tau minus epsilon tau from 0 to infinity plus. Okay, at infinity this is 0, at 0 this is 1. So this is equal to the limit as epsilon goes to 0 of minus 1 over I minus epsilon, which is the limit as epsilon goes to 0, rationalizing the denominator, epsilon squared omega k minus maybe eg squared plus epsilon squared plus I omega k g over right? Just rationalizing the denominator. What do these functions look like as a function of omega?
The delta function and the derivative of the delta.
Yeah, sort of. Let's look at them before we take the limit as epsilon, for a finite epsilon. What's the function as a function of omega k for fixed value of epsilon? It's a Lorentzian, right? A Lorentzian, and what is the width of the Lorentzian? Approximately. This is at omega eg, by the way. Sorry, I should have done. So let's say as a function of the determinant. What's the width of that delta, of that Lorentzian?
Epsilon.
It's around epsilon, right? And the height here is 1 over epsilon. And what's the area under that curve? Do you know? Pi, turns out. The area under this curve is pi. And this guy is like our dispersive line shape, right? That we had the imaginary part of that. So, as David said, in the limit that this goes to 0, this thing looks like a delta function. And it has an area pi underneath it, so the strength of the delta function is pi. Notice, if this were from minus infinity to plus infinity, then you should know that that thing is a delta function with a area underneath it of 2 pi. So this is like a half a delta function, which is why this is pi and not 2 pi, okay? But this fact that I don't go from minus infinity to plus infinity means that I have this extra imaginary piece here, which I wouldn't have had this gone from minus infinity to infinity. This is the Fourier transform of a step function, rather than the Fourier transform of a line. So what happens to this thing as epsilon goes to 0? Well, as epsilon gets smaller and smaller, this thing becomes steeper and steeper and steeper, right? Because the width of this is also epsilon. And this thing is known as Cauchy's principal part. And like the delta function, it only makes sense inside an integral. So the Cauchy's principal part P sub c, from minus infinity to infinity, is the limit as epsilon goes to 0, minus infinity to minus epsilon goes to 0 from the positive side, f of x over x dx plus the integral from epsilon to infinity f of x. It's a way of taking out the singularity where this thing blows up exactly at the origin. So if I were to look at the convolution of this dispersive thing with whatever else is in the integral, and I take the limit as it goes to 0, it multiplies it by 1 over x, but it just slices out the set of measure 0 exactly at the origin where that thing, that's Cauchy's principal part. Okay. So, with that said, we can come back over here. This was my zeta omega k minus omega g. And so we have the answer. The answer is this. This is equal to minus gamma over 2 minus I delta C e g of 0. Where gamma over 2 is equal to this thing evaluated at omega eg times pi. I'll come back to the delta. Again, I just plugged in for this the delta function through the integral, and it picks up that value at pi. So that tells me that gamma is equal to 2 pi which was 2 pi times this guy squared times the density of states, which you should recognize as Fermi's golden rule. Fermi's golden rule comes out of the Wigner-Weishaus calculation. It says that the rate of transition is proportional to the square of the coupling matrix element times the density of states. And when you put all that together, you get that gamma is equal to 4/3 VEG squared over H bar, omega over C cubed. that is Einstein 8 coefficient. Okay. What about this delta business? Well, that's coming from this dispersive effect. And when I plug in that Cauchy's principal part in there, I get the following. How do you interpret that? Any thoughts?
Is it analogous to the lamp shift?
It is the lamp shift. It is a piece of the lamp shift. You know, the full lamp shift has to take into account all the neglected terms beyond the rotating wave approximation and the two-level approximation. But this, what is this thing? Well, it's a frequency. I can think about it as an energy if I put in energy. It's saying that, you know, if I come back over here to this, there is an additional phase. So that's what this tells me. The solution to this is that whatever the initial thing is, right, the probability is the square of the amplitude. And as expected, it decays with the rate down. But what is this? Well, it's an additional phase that is accumulated, and we can always think about that additional phase as an energy level shift, right? So this is this change in the energy, T in units of h bar. Is that clear? So given that, is this the form that you would expect the energy shift on the atom to take due to its interaction with the quantized electromagnetic field? What form wouldn't you expect it to take?
Perturbation.
Perturbation theory. This is second order perturbation theory. To first order, there is no dipole moment, right? To first order, there's no dipole moment, but to second order, there is. And it's related to the square of the interaction matrix element squared over the energy denominator. Beautiful, we love that. It all comes out as expected. This is like the light shift, but it's the light shift due to the vacuum. Remember, we saw a contribution to the light shift, which I call the lamp shift, in the dispersive regime, in the context of the atom in the cavity, right? And this is just that. And this comes out of Wigner-Weisskopf, but it wouldn't come out of Fermi's golden rule. You needed to do the whole thing to see that piece. Yeah, because
So basically, every time we observe energy, it's shifted because of vacuum.
that's right. So the actual energy levels in the atom have to include its coupling So the actual spectrum is not just the solution to the Schrödinger equation or even the Dirac equation without the coupling to the vacuum, right? And in fact, it's one of the ways that atomic physicists have looked for tests of fundamental physics. I don't know if you were here, I think it was last spring when Dave DeMille gave our colloquium. And he talked about looking for the Hermann electric dipole moment and how, so they were looking for, basically corrections to electroweak theory. You have to really, all the fundamental fields are always there in some sense, the vacuum, and it affects the spectrum, the ambiguous. So if you can do precision spectroscopy and measure the energy differences between intervals to extreme precision, you can make tests of fundamental physics. Great. All right. We did it.